Welcome everyone to another episode of CUDA Mode. I'm super glad we have two returning speakers like Georgie and Jake. I believe you're the first returning speakers that were not part of the core mod team. So it's really a pleasure to have you back. So last time Georgie and Jake were here to talk to us about their fork of LLMC, which was Karpathy's work and forking it to LLMCPP. I think that talk was very well received. And so they're back, and this time they're going to talk to us about the scan algorithm and how to make it pseudo-light. One of the things that makes scan really interesting for machine learning applications is that it's sort of a core foundation of a lot of modern architectures like Mamba. So if you're trying to understand that work, I would imagine this would be an awesome prerequisite that would make your life significantly easier. So yeah, so without further ado, Georgie and Jake, please take it from here.
Thanks, Mark. Georgie, you want to take it to the next slide? So yeah, scan is my favorite algorithm, bar none, no questions asked. And that's because it is just one of the singular most powerful algorithms in the realm of parallel computing. And its superpower and why it's so awesome is because it takes problems that look like you couldn't do them in parallel, like they're inherently sequential or serial, and scan just magics it and turns it into something that you can do in parallel. Um, I have this representation here, but it's this idea you have this sequence of things, whether it's an array of integers or whatever, and you're doing some sort of operation to reduce those things. But instead of it just being reducing all those things to a single value, you kind of want all the intermediate state along the way as you go. And so Izzat talked about this awesome algorithm, and we could have 20 lectures about this algorithm because it's so cool. And so, for more deep dive and kind of into the background, go back and watch Izzat's talk. And we're really going to focus on today, basically taking those foundations and say, okay, now how do we take scan and do it literally as fast as possible on the GPU? And what we're going to introduce today, if you're not familiar with it, is this concept of speed-of-light analysis. Whenever you're doing performance, this is how internally NVIDIA, you're going to hear people say speed-of-light or SOL all the time, because this is how we think about things. And so it's a really important foundational concept when you're doing any kind of performance sensitive stuff, to think about speed-of-light and how close you are to that. And so today on GPUs, the fastest way to do scan is with the decoupled lookback algorithm. So we're going to tell you about that. And like I said, making scan as fast as physically possible. And not only are we going to tell you how to implement this, but also we're going to show you that you don't need to implement it, that we already have given you all these different foundational tools that if you need scan or building blocks to do some kind of custom scan stuff, well, we've got stuff for you in the CUDA core libraries. Next slide. And so very quickly, Mark had referred to our previous talk where we talked about this a bit more in depth. And so I'm going to go over this quite quickly. But the CUDA core compute libraries, or CCCL, is a collection of a few different open source C++ libraries. Our GitHub repositories on the bottom there, but they're also available as part of just the CUDA toolkit by default. And today we're really going to focus in on the cub part of CCCL that provides these lower level GPU parallel algorithm building blocks. Go next slide. I also showed you this slide last time that kind of shows you this spectrum of different tools, from higher level to lower level, and how productive they are versus how much control they give you. And we have things at all these different points on the spectrum. But today, advance to the next slide, we're going to focus on the scan parts here. And so in cub, we have device scan, block scan, warp scan, and decoupled lookback abstractions. These things are used to also implement thrust inclusive scan and exclusive scan. And so one of the points we really want to drive home here is that while everyone here should definitely learn how to implement parallel scan, it's just a fantastic exercise in CUDA and parallel computing in general. But when you need this in production code, you want to be using one of these abstractions from CCCL, that you aren't wanting to implement these things yourselves because it as we're about to see, can be quite challenging to get it exactly right and go as fast as possible. And plus, I can say with 100% confidence that our scan in CCCL and Cub is the fastest you can go. With 100% certainty, I can tell you that you cannot implement scan faster than what we have. And that isn't a challenge to goad someone into trying to do so.
I was gonna say, like, would this also be true for consumer GPUs? Because like I think that
Yes.
we might want to throw the gauntlet here. Okay.
Absolutely. If you can make it faster, I mean, there may be GPUs we haven't tuned it to as extensively as others, but that's a problem that can be solvable easily enough. And so I want to, I made that claim quite confidently, and I want to provide justification for why I can say that so confidently. And to do that, I'm going to hand it off to Georgie, who is going to introduce you to this concept of speed of light performance analysis and really walk you through the gory details to the point where you will, I think, believe me when I say you cannot go faster than what we have here. So, Georgie, take it away.
So we actually already have our first question, Georgie, before you even started talking, which is like,
Go for
does
it.
it like XLA automatically make scan fast? So maybe just like, yeah.
Yeah, so there's no magic here. And that's true of pretty much anything in the core libraries. Like, we believe in making things easy and convenient, but we don't believe in magic. And so we provide, you know, an algorithm that you give it the inputs, and there's, you know, whether it's scan or reduce or whatever algorithm, it does what it says on the tin, right? Like it does a device scan, and it does it in parallel with your inputs and to your outputs. And there's no like fancy compiler trying to do magic for you.
Okay, so today we'll be talking about various CUDA implementations of prefix sum. And to compare performance of these implementations, we need some metric. And one of the frequently used metrics for performance comparison is speedup. But speedup is rarely the right metric because it doesn't tell you how fast a given algorithm should perform. For instance, on the slide, you can see two kernels. Both kernels copy a gigabyte of data. And first kernel performs a copy using a single thread, whereas the second kernel copies data by a thread block. And naturally, the second kernel is almost 200 times faster than the first one. The first reaction to this speedup is that we should be using the second kernel. But in practice, the second kernel only reaches 2% of the peak bandwidth. So both kernels are equally inefficient. And at NVIDIA, we rarely use speedup. Instead, we tend to identify the theoretical peak performance limit for a given algorithm. We call this theoretical limit speed of light. Then we can evaluate a given algorithm by looking what percentage of speed of light it achieves. This is convenient in many ways. For instance, now we don't need another algorithm to understand if our code is fast. Understanding how close a given code to speed of light is sufficient. Besides that, speed of light tells us when to stop optimizing the code. Just like in the example I mentioned, the 200x speedup suggests that we can stop optimizing. But when we look at 2% speed of light, reaction is quite opposite. And to showcase speed of light analysis on a concrete example, let's try to figure out speed of light for scan. And to estimate the speed of light for scan, we have to understand if algorithm is compute or memory bound. One of the metrics that can help us do that is arithmetic intensity. The idea is that we divide the number of arithmetic operations by the number of bytes we have to load and store to memory. Here, for instance, first code performs only one arithmetic operation. It adds two floating point values. One of the values is in memory, so we load it and then store the result back. This gives us two memory operations, one read and one write, of 4 bytes. Second code performs the same number of arithmetic operations, but loads one extra float. So the arithmetic intensity is lower. We can then plot performance as a function of arithmetic intensity. This plot is going to be bound by two limits. First limit is the peak compute that a given GPU can achieve. Second limit is the peak memory bandwidth. The point where two limits meet separates memory-bound algorithms from the compute-bound ones. For instance, copy algorithm will be on the left side of the spectrum because it doesn't do any arithmetic. On the right side, you can find matrix multiplication because it performs much more compute per byte. And arithmetic intensity for prefix sum is much closer to a copy than to matrix multiplication. In fact, on A6008, we need about 200x more arithmetic operations per each element to put prefix sum into compute-bound category. Now, this information allows us to ignore the compute part of prefix sum when analyzing speed of light. So now we can analyze scan purely from the memory perspective. First, scan must read each input element. This gives us n memory operations. Then scan must write an element back to memory. This overall gives us a lower limit of 2n memory operations. So speed of light for prefix sum should essentially match the performance of memcopy. Now, let's try to analyze various scan implementations from the...
So I already see a few interesting questions in chat. So Byron is asking, like, he's asking about, like, how does the scan implementation work in PyTorch today? Like, does it like use, like, leverage a lot of these parallel scan ideas?
I think it's using Cub.
I believe so as well. If not Cub, then Thrust.
I also had a question that's like maybe more related to the previous slide. Actually, wait, there's another question. This estimate is for scan from DRAM, right? You'd have, if you have data in L2, you'd be much better.
Sure. We analyze this from the perspective you have clear cache, or if you can imagine a large input, for instance, you have 20 gigabytes to scan. In this case, L2 cache is much lower, so you can't feed the whole input, and like presence of data in cache doesn't matter. It'll be like evicted soon.
I see. So do you mind going to the previous slide for a sec?
Yeah, sure.
The one before, maybe two before. It was the one where you were showing the speed. Yeah, this one. So this one's maybe this is more of a cultural question, not a technical one, but I was curious because like I've often seen, especially like as working on performance at Meta, like you see people sort of saying, I made something 10% faster versus I made something 300x faster. And usually I sort of just shrug my shoulders. I'm like, okay, faster is good. I'm wondering like the sort of NVIDIA performance culture, like do people just generally expect that you provide speed of light? And like, is this sort of like the way performance is measured internally for promotions and stuff?
Yeah, exactly. So we look at problems from the speed of light perspective, exactly for this purpose. Like kernel on the right is like 200x faster. Like how faster can it be? And 200x is a lot of speed up, but both are terrible. So like, is that speed up is not sufficient to understand how far are you from the ideal limit that you're trying to achieve.
Sweet, thank you. Yeah, I can let you go back to the slides.
Sure. So, okay, now let's try analyzing various scan implementations from the speed of light perspective. In our algorithm performs close to speed of light, it means it's optimal, right? Our work is done. If algorithm is far from speed of light, it means we are missing something. Anyways, let's consider three algorithms. Reduced length scan, hierarchical, and stream. And these algorithms were covered in previous CUDA mod talk, so I won't spend your time explaining them today, but it might be helpful to recap some of the key properties of these algorithms. So reduced length scan performs 3n memory operations. This extra memory operation means that algorithm can't achieve more than 66% of speed of light. On the other side, you can see that this theoretical limit is quite close to the achieved throughput. So our prediction is correct, and we can proceed to the next algorithm. Okay, let's move on to hierarchical scan. This algorithm reads and writes data twice, which leads to 4n memory accesses. Following this logic, this algorithm can't achieve better than 50% speed of light. As you can see, the prediction is quite close again. So let's carry on. And the last algorithm is stream. But something is wrong here, right? The algorithm performs only 2 memory accesses. It should be faster than both reduced length scan and hierarchical. But we see that it can't even achieve 1% speed of light. So let's figure out why. As Izzat explained in the previous talk, stream serializes all thread blocks. This serialization happens because each thread block waits for a previous block to produce inclusive aggregate. Let's try to come up with a speed of light model for this algorithm. Talking about overall memory movements, stream is optimal because it only loads and stores data once. But unlike previous algorithms, this that we discussed, stream performance is not bound by memory bandwidth, it's bound by memory latency. Let me clarify this point. We know that thread block A will store inclusive prefix into memory. We also know that thread block B will wait for that store. The number of cycles it takes between block A storing something and block B observing this is called message passing latency. I choose some random number, let's say message passing takes 500 cycles. Knowing the message passing latency and the GPU frequency, we can convert clocks into seconds. Because all thread blocks are serialized, we can now compute how many message passings can happen each second. Now, when we have message passing throughput, we can turn this into bandwidth. We know that a given block loads a tile and then stores it back into global memory. So we have 2 tile bytes divided by latency. This leads to about 2% peak bandwidth that this algorithm can achieve in theory. The throughput is so low because GPUs are not optimized for latency, they are optimized for throughput. But what I want to bring your attention to is the gap between expected and achieved throughput. For other algorithms, we were quite close to theoretical limit, but not in this case. So what's wrong? Is there a flaw in speed of light model or something is wrong with the implementation? Let's take a look.
So Georgie, before you start, I had a quick question about like basically how to produce this, just because like presumably because like speed of light, like this is not something like a profiler will really help you produce. This like really requires that one, you understand like the algorithmic properties of your model, like you're like writing some math formulas and thinking things through. So how do you not delude yourself just because like a piece of paper won't tell you that you're wrong? So I'm curious how you go about this.
Yeah, that's the iterative process, right? At this stage, we're like, let's build our intuition about this model. Like, it seems reasonable, right? But now let's verify, and we see this gap. So our prediction is much higher than our actual code. So let's see through code changes if like code is wrong or model is wrong. It's like we're trying to do that right now.
Interesting. Okay, got it.
I want to add something here. Yeah, go ahead, Jake.
Okay, I was just gonna say, like, there isn't, and I saw the question about does speed of light analysis use some math to calculate the peak performance under the hood? There's no fancy math here. Really, what you're looking at, it's really a 2-stage decision process. You look at your algorithm, you decide, am I memory bound? Am I compute bound? Okay, if I'm memory bound, then I go to the white paper, I look up, okay, what is the max bandwidth here? And then am I achieving that? Or what fraction of that am I achieving? Alternatively, I'm a compute bound. It's like, okay, what is the max throughput in flops? And then I look at, okay, what am I achieving? And so like the math is quite simple. It's really like speed of light analysis is napkin math. Like it's very like pretty high level and quick and dirty. And so there's really no magic to it really. It's just compute bound, memory bound, okay, memory bandwidth, compute throughput. That's the first order approximation.
And to add to that, there is one more term usually in this space used. It's called roofline analysis for a given algorithm. If you go and look into many supercomputing papers, historically, they would start for a given algorithm to understand, hey, what is the roofline analysis? How does it scale? How does it go up when you change the component? And how do you actually move towards a roofline numbers that you can hit? So there are many ways to do it. So I think recommending checking on roofline analysis scripts would actually be the good start. And PMPP book also has this.
Yeah, let's carry on. Let's focus on the message passing part of stream. There's actually.
There's more questions actually. I think people seem very engaged. Basically, Eric is asking, like, where do I actually look up the max bandwidth for GPUs that are not in the top model? So for example, he's saying that he can find basically like on public sheets that like he can know what the max bandwidth is for 4090, but not for a 4070 or for a 4060. So how can you sort of, I guess, measure this? Or yeah.
I think there are two ways. First is like trying to find a product release page on NVIDIA site that would say like, here's A100, here's the peak bandwidth, and you take that. But if this is not available, it's always a good recommendation to try and run Stream benchmark on your machine whenever you are. Like Stream is a industry standard for measuring achievable bandwidth. I hope this answered the question.
Like, sorry, you mean literally the stream algorithm that you're covering right now is what you use for?
That's why the name
overloaded term.
Yeah, that's why stream is not the best name for this algorithm. In many papers, it's actually called chain scan. So by stream, it's also a conventional term for a benchmark that streams data from one memory location into another memory location. So it's like a known benchmark in HPC area. It's called stream. It's basically doing a copy, vector add, and something else, and shows you the performance of this.
Got it. And so, like, I guess if people are interested in running some of these scripts like on their like local, because I think especially for consumer GPUs, like the CPUs might be very different, and maybe people's perf characteristics will be different. I guess my question to either Jake or Georgie is like, is there any sort of like set of scripts that you recommend people take a look to sort of know all these numbers for their GPUs quite easily? Is there like perhaps a repo that aggregates like some of this data?
There's a repo NVIDIA.org that you can find that does stream on CUDA. So like it shows you bandwidth, like the right way to compute bandwidth on your GPU.
Cool. Yeah, I think I myself and probably a lot of other people in chat would probably appreciate a link after this. So
sure. Yeah. Any other questions on this point?
No, just keep going. Like I think I'm probably going to keep interrupting you. So
it's fine. Please do. So let's focus on the code on the left. The stream part is suggested as highlighted. So there's actually a bug in that code. So I'll give you a moment to spot it. Okay, so there's actually no memory fence between atomic add and volatile read of scan value. And both atomic add and volatile read are relaxed memory operations. That means that this can be reordered by both compiler and hardware. So this will lead to a situation on the diagram. Subsequent thread will observe a flag, assume that it's safe to read the value, but value was not written yet. This means that we will add some random prefix instead of what predecessor thread block intended to pass. And to avoid this kind of memory ordering issues, you should be using std_atomic instead. When using CUDA std_atomic, we can clearly state that the flag load has acquiring semantics. In this case, loading scan value can't get reordered before loading flag, just what we wanted. Now, that the code is functionally sound, let's return to the original question. Why is expected throughput so far away from the achieved one? The issue is that our speed of light analysis was based on message passing latency. but the code is doing much more than that. Let me clarify what I mean. So here's what code is doing. We start by loading a flag of predecessor thread block. Then we issue a memory barrier to ensure memory ordering. Then we load message of the predecessor thread block, and then we store our inclusive aggregate, issue another fence, and finally update a flag to let subsequent thread block know that the message can be consumed. If you remember, our definition of message passing was a bit different. We defined latency of message passing as the time it takes between one thread storing something and another thread observing the store. But here we have two stores, two loads, and two more memory fences. How can we make our code conform to the definition of message passing? Well, we can combine message and flag into a single architectural word. If aggregate is, say, 32 bits wide, we can use 64 bits wide type to fit both message and flag. Let's call this combination of flag and message a tile state. Now we can simply load predecessor tile states without memory fences. Same applies to storing the tile state. There is no need in fences because both message and flag are stored as a single memory operation. And single architectural word optimization provided about 3x speedup, and that leads us much closer to speed of light. We now reach 1.8% speed of light, while our theoretical limit was 2.4. Although we're much closer, it seems that there's still room for improvement. But what's limiting our implementation now? Our kernel consists of 4 stages. We start by loading tile, then performing prefix sum, message passing, and then finally storing the result back to global memory. Stores and loads are trivial, and message passing is efficient now. So the only thing that's left in the manually written block prefix sum, I'd guess that it's the only part that might be causing inefficiencies. So we can try and replace it with cap block scan. That we'll assume to be efficient for now. Now, let's replace manually written prefix sum with cap. Cap is one of the core libraries provided with every CUDA compiler. So if you use CUDA, cap is available to you out of the box. Now, let's dive into cooperative API of cap. Cooperative API is invoked by multiple threads to collaborate on a single problem. Cap block scan has to be invoked by all threads of a given thread block. Each thread provides a piece of input and gets a piece of output. Let's take a look at a concrete example. We'll start with a block load algorithm. In general, to use cap block scope algorithms, we start by instantiating a struct. Here we provide a type of values we are about to load, which is int in our case. Then we specify the thread block size, compile time. All block algorithms provide a member type called temp storage, and we use this type to allocate shared memory that threads will use for communication. Once we have load object, we can cooperatively invoke it. Note that every thread provides the same pointer, but loads different values. Let's take a look at what happens when we have multiple thread blocks. Input is partitioned into tiles, and each thread block processes a single tile. Tile size is the number of items per thread multiplied by the thread block size. Output of the block load is left in registers. Now that we have input data loaded, we can execute inclusive sum. The tile is already partitioned between threads, so we can just pass it to the block scan. After block scan, each thread has part of the result in registers. Later, we use block store to put this result from registers back to global memory. And overall, replacing manual implementation of load, scan, and store with cap cooperative algorithms got us better performance. Now we are much closer to speed of light for stream algorithm. But can we do any better? To answer this question, let's return to the speed of light model we built for stream. If you take a look at the throughput computation, you'll see that tile size is in the numerator of the ratio. This means that increasing tile size should increase throughput. We used 1 item per thread so far, and that got us 2% theoretical peak. But if we increase the items per thread to 23, we should be getting 49% throughput. 23 is not a magical number. I'll explain why we selected it later. But regardless, let's try to build some intuition for why increasing tile size increases throughput. Let me bring your attention to the diagram on the right. After loading input, we have to wait before message propagates through the memory subsystem. Instead of just waiting for message to propagate, we can as well load more data. There's still enough time left, so loading extra items is basically free. Let's see if benchmarks verify our intuition. Since CAP API is parameterized on the number of items per thread, we can change a single line of code to affect tile size. Here, I increase the tile size to have 23 items per thread. I don't have to re-implement any of the algorithms. It's the only change I've made. Overall, it gives us 11% throughput, which is a huge improvement compared to 2% we used to have. But still, new theoretical limit is 49. Why are we so far? Let's try to figure out. Let's consider memory accesses across threads of a thread block. Block load is very simple. All it does is loading data at a stride. This means that thread reads data 23 elements apart. Memory is loaded at a granularity of sectors, which is 32 bytes. But in our case, each thread reads data that's 92 bytes apart. In other words, none of the sector bytes are reused, and each warp is loading 32 sectors. This means we load 10 times more data than we need, and this is inefficient. CAP provides you a way to get rid of this strided loads. We can tell CAP to load data in coalesced manner, and then transpose it to restore the original order. Coalesced loads are going to be more efficient. The only issue is that transposition requires a lot of shared memory. Anyways, let's take a look at our performance now. Okay, good. So with only 2 lines changed, we got up to 43% throughput. We've got about 4x speed up, which brings us much closer to the theoretical throughput limit of 49%. So the scheme works, right? Like we can just keep increasing the tile size and we'll reach speed of light, right? Not really. So let's see what happens with our kernel when we keep increasing the tile size. On the right, you can see 2 graphs. One shows how shared memory size depends on the items per thread for a fixed block size. As you can see, using 24 items per thread get us out of the architecture-independent shared memory limit of 48 kilobytes. That means that some GPUs will not be able to provide enough shared memory. Let's say you target a specific GPU and can go beyond 48 kilobytes limit. In this case, we can use 24 items per thread, but if we go any further, the occupancy drops to 0. That means that SM can't fit even a single thread block. In other words, this is as far as we can get with this serialization. To get higher throughput, we need to get rid of this serialization. So let's try to do that. One of the ways to work around the serialization is called decoupled loopback. And to explain decoupled loopback, let's compare it with stream. In stream, each thread block waits for the predecessor thread block to produce inclusive result. Decoupled loopback, on the other hand, waits for partial results of predecessor thread blocks and then combines them locally. Let's see how this helps us get away from being latency bound. On this slide, you can find a more detailed comparison. In the stream case, block 2 waits for block 1. The update of tile state from block 1 becomes visible to block 2 after message passing latency. At this point, block 2 updates its tile state, and this update becomes visible to block 3 after the same message passing latency. Contrast this with the decoupled loopback. Here, block 3 reads states of block 2 and block 1 at the same time. Block 3 combines inclusive aggregate from block 1 with partial aggregate from block 2, which gives block 3 inclusive prefix. To make this process a bit easier to understand, let's go through the decoupled lookback step by step. Here we start with 3 thread blocks. Each thread block adds tile reduction to accumulator. Then block 1 and block 3 store their tile states to global memory. Block 3 then reads tile state of block 2, but block 2 hasn't updated the global state yet. So block 3 reads invalid data. Now block 2 manages to update tile state and reads tile state of block 1. Now block 3 finally pulls valid state of block 2 and adds it to its accumulator. And here we reach a very important point. As block 2 was writing its inclusive result into global memory, block 3 already pulled inclusive result from block 1 and combined it with its accumulator. This means that block 3 got inclusive prefix at the same time as block 2 stored it. So propagation of inclusive prefix is not serialized, it's decoupled. One thing I haven't mentioned is that instead of loading a single tile state at a time, we actually load 32 tile states. We call this a loopback window. The motivation is that we read a sector granularity anyways, so we can get more tile states at the price of loading a single tile. The downside of this approach is caused by significant overlap in loopback windows of consecutive blocks. This overlap leads to each memory location being read by about 32 CTAs at a time. This creates a lot of contention in the memory subsystem, so we need some sort of back-off mechanism. And to address this contention, CAP implements various back-off mechanisms in the following loop. Simplest back-off scheme is just having a fixed delay. We can always also try exponentially increasing the delay each time we load invalid tail state. But which approach should we use? What are the optimal delays? Without tuning, it's hard to tell. So we extensively tune CAP on various workloads and GPUs to select the best back-off mechanism for each use case. Good news is that we spend a lot of time thinking about this, so you don't have to. CAP exposes decoupled lookback, so all 3 aspects of selecting the lookback window, delay scheme, etc. are hidden behind a high-level abstraction. Let's take a closer look at decoupled lookback. We start by constructing a tile prefix operation. One of the first things that are abstracted out is the tile index computation. As you may know, CUDA doesn't give you any guarantees on the order of launching thread blocks. Conventional way to get runtime order of thread blocks is using atomic head. CAP relies on certain undefined behaviors, so providing you with a tile index computation that outperforms atomic head. Now, first tile doesn't have to look back, so we can immediately set inclusive state. Subsequent tiles invoke prefix call operator cooperatively by the first work. This operator returns the exclusive prefix, meaning that it doesn't incorporate aggregate of the current block. Let's take a look at how decoupled lookback affected performance. Here's the performance of the final kernel. All we did was replacing chain scan part with decoupled lookback. With this change, finally managed to achieve 86% bandwidth, which is about twice as fast as our best take on stream. If you now compare our solution with CAP, you'll see that CAP is still faster. But why is that? The only difference with CAP device scan is that we extensively tune it. On this slide, you can see a typical search space in which we search optimal tuning parameters. There are multiple ways to load data, multiple cache modifiers we have to try, let alone items per thread, thread block sizes, etc. Overall, search space for scan is about 2 billion variants per data type per GPU. We apply optimizations.
I'm sorry, George, this is a pretty crazy picture. Like, do you mind just helping us read it a bit? Like,
Yeah.
like what are the colors? What are, yeah.
So color is speed up here. and you see complete variant going through different tuning parameters, right? Like you can have one tuning variant that chooses to transpose input and then apply some cache modifier like streaming or LDG, etc. Then we select complete items per thread, thread block size, and overall it's like a selection between multiple axes, right? So each line is different tuning variant, leading to a different speed up on the right. Overall, there should be 2 billion lines on that plot. But as you can imagine, it's not reasonable to exhaust the full search space. So we apply some optimizations to find optimal tuning parameters.
Got it. Thank you.
Mm-hmm. Okay, so on this slide, you can see how CAP compares to various algorithms we covered in today's talk. We get about 90% bandwidth, which is practical limit we reach by tuning our algorithms. Overall, all the efforts we put into CAP algorithms lead to speed of light performance on various data types and GPUs. So I'm confident you can't get any faster than CAP. I hope we managed to illustrate advantages of the speed of light approach to performance analysis. The speed of light use speed of light to discover algorithm bottlenecks and optimization opportunities. Speed of light also helps understand when to stop optimizing your code. But if there was a single takeaway for today's talk, it'd be the following. Implement fundamental algorithms. It's a good practice, but because it helps you build intuition about GPU programming. But as soon as you need a fundamental algorithm in production code, you should be using core libraries. And if for any reason our abstractions do not work for you, please let us know. You can always file an issue on GitHub or reach out in our Discord channel. So that's all we want to share today.
Sweet. Thank you so much, Georgie. Thank you so much, Jake. And okay, Drexel is saying NVIDIA stock still room to go up. So I think this is this is good. Yeah, I'm gonna go over questions in chat. Let's see. I guess like Vikram, maybe I'll put you on the spot. You're mentioning that you're mentioning like a paper that you thought might be helpful. Like is there sort of like any core things you think people should get out of reading that paper?
George and Jake, I referred Duane Merrill's decouple look back algorithm paper. You want to comment?
Yeah, sure. So paper goes into more details, more thorough performance comparison. So it doesn't hurt to read it.
Yeah. So Duane Merrill is part of NVIDIA research, and he is one of the persons who developed the decoupled look-back scan algorithm back in 2016 that you're learning today. So it actually gives you like the intuition behind how to create a theoretical boundness for scan algorithm and what are the limitations of the regular stream-based scan algorithm. The paper is a bit more complex, but I think what Georgie and Jake has done is a fantastic job on making it very simple to understand. So if you want to go really, really deep into the algorithm, the bounds and other things, then I think I really recommend reading that paper.
Agreed. I think one thing to point out too that has kind of advanced since that paper is that Duane and Michael's original paper, it didn't talk about any of the back off stuff. Like the original decoupled look back didn't have back off, and that's actually a new thing that Georgie discovered actually, that on latest architectures that L2 latency has increased, and so it increased the importance of having that back off. And so if you read that and are asking where's the back off part, it's not there. That's a newer addition.
So I had another question regarding the parameter search. Like I saw, Jake, you were saying this is using some genetic algorithm magic. I guess like maybe my Uber level question is like, for a lot of like, I guess like when it comes to any sort of like basically hyperparameter tuning, like there's certainly always a lot. I'm seeing people do like grid searches. I see some people use like probabilistic methods to sample. You're mentioning a genetic algorithm. Is there sort of like a general consensus on how this stuff should be done within NVIDIA, or is it also basically different people have different opinions, sort of thing?
I can answer this question. We're using a tool that's an internal tool today, that does, like you said, this hyperparameter search space, for usually for like performance optimization kinds of things, but it's more general than that. That's currently a proprietary internal tool. We are working on getting them to open source or at least release it externally. But yeah, it's a great tool. I'm sure people have plenty, people always have opinions on the best way to do things. But this tool is increasingly popularly used internally, and yeah, it does some genetic algorithm search space to try and find local optimals in this hyperparameter tuning space.
So Drexel is asking, do you even do this kind of search on consumer cards as well?
Yes,
Interesting.
yes, we do.
Okay, and I see Eric asking, okay, Drexel is responding bug. So it's cool. So Eric is asking, so even with extensive tuning, isn't there admittedly a small variation that depends on example how well the cooling works for your specific GPU, or does temperature mostly affect just compute, not memory, so it wouldn't matter here?
So yeah, when we say, you can't go any faster, like within the domain of like plus or minus 1 to 2%, right? Like there are hardware like hardware differences, thermal differences that can account for, things that we would normally just kind of consider more or less noise. One thing that we'll point out though is that the methods and statistical methods we use to compare, is this set of tuning parameters faster than this set of tuning parameters, kind of are statistically robust to many forms of that noise, that even if two GPUs like are thermally throttled, like we're doing many collections of samples and really looking at the full distribution of times, that like we might collect 1,000 samples for a given set of tuning parameters and really look at the distribution of those things, because it may be multimodal. Like performance data is never just a normal bell graph, like never ever. Like we could do a whole talk on just that point. So if you're using just averages and standard deviation for performance stuff, we could probably do a separate talk just on why you shouldn't do that. But yeah, like it's impossible to be 100% perfect because of the just physical laws of the universe and entropy on this. But like I think do as much as statistics basically allows to make sure that we can be confident in the answer we come up with at the end of the day. George, I don't know if you want to add anything to that.
No, I think it's a great answer.
Cool.
I guess related to that, like we've had like a lot of people in the Discord group like ask questions about like how can I tune the specific model better on my consumer GPU? Generally, the answer, like at least like anecdotally, like I've noticed that like things like, for example, Triton tend to just be significantly faster on A100s and like H100s. Like the relative speed ups tend to be more substantial. The versus on consumer GPUs, and so people don't really have a good sense of like what are the things that I should be paying particular attention to if I'm doing performance tuning on consumer GPUs. I'm wondering if you sort of like have a good sense of, I guess, like the first things you'd look for when you're optimizing a workload on a 4090 versus like A100. What were the things you'd mostly watch out for outside of the obvious VRAM?
Yeah, I mean the first order things are like what I was saying at the beginning, right? You just look at the peak bandwidth and the peak compute, and if your problem's memory bound, you care about the peak bandwidth, and if your problem's compute bound, you look at the compute throughput. And if you need to get fancier than that, then it's hard to speak, I guess, generally, if you're needing to go layers deeper than just looking at the top level speeds and feeds. I don't know, Georgie, do you have a better answer than that?
I'm sorry, I missed that question. Could you repeat?
I think Mark was just asking, like, is there anything different to look for when you're optimizing performance on consumer GPUs versus like top end data center GPUs?
I think from the search space exhaustion point of view, there is no difference. Like as soon as you throw an optimization method on searching tuning parameters, it's the same thing. But when you are talking about actual code changes, like not tuning, but code changes, you can obviously use data center specific features, right? For instance, H100 will give you clusters, but consumer GPU doesn't have clusters. So maybe you at least should get acquainted with set of features that production quality GPU provides you and see if those can be applied to your particular workload.
Right,
with
right. And so I think
another
like the
example.
answer is it depends. Like when you
Yeah.
get past the first level of speeds and feeds, it's really dependent on like what are you doing, what hardware features can you take advantage of, and things like that. But truth be told, like just the surface level speeds and feeds, like that is good enough for 80% of things, I would say, like easily. Just looking at how much data am I moving, how fast am I moving it, and how does that compare to just what the raw sequential bandwidth would be. And if you're getting like 80-90% of that, then you know your job is basically done.
So another question is from Andy Lowe. I'll paraphrase it a bit, just because like I'll paraphrase it a lot, just because like I have a similar question, which is like basically like the diversity of GPUs makes it very difficult to do any sort of like automated performance benchmarking in CI. So for example, like having A100s in CI, it's like how GPU rich do you have to be to do that? So like in repos that I work with, we use A10Gs, which are already quite pricey. And then what I end up doing actually, and this is like I unironically do this, which is if there's like I know some people in CUDA mode have a 4070 or a 4060, I'll tell them, could you please like run this code and list like post the numbers on this GitHub issue? So I'm sort of like wondering, is there like a better way of doing this outside of like potato farming GPUs?
Well, I'll give you the biased answer first. The biased answer is this is a good reason why you should opt to use stuff from CCCL is because we've already done a ton of that work to test on a billion different GPUs. Because we generally have access to those things. Though you might be surprised how hard it is for us to get certain GPUs sometimes as well. So it's not always that much better inside. And apart from that, which I recognize is a bit of a non-answer. Yeah, it's hard. I think it depends on how wide of a net you want to cast, right? Like if you are solving a problem that you want to be as fast for your particular workstation GPU, then it's fine to fit to that. And if you're building a library that you want tons of people to be able to use on tons of different kinds of GPUs and always be speed of light, then there really is no substitute for trying in as many different GPUs as you can. And barring that, using libraries or abstractions that have already done that work for you whenever possible, I think would be the pragmatic answer, I guess.
I'll celebrate a bit on this part. So another suggestion would be to outsource this problem a bit. So if you are developing open source projects like CCL, for instance, what we do is we actually open source our tuning infrastructure so that if you have a workload or a GPU and CCL doesn't perform well on that, you can just contribute a tuning, contribute a new workload we haven't considered, and we encourage you to do that. So this somewhat addresses the problem that like someone has a unique use case, unique hardware combination, and we do not perform well there. But
That's a very good point.
Yeah, but so far we like haven't received any of this, meaning that like we have speed of light everywhere.
I guess y'all are both like definitely challenging folks in CUDA mode. So yeah, so I will say like if you are optimizing like a workload on consumer GPUs and it's really slow, I think I heard Jake and Georgie volunteer to like help us like optimize those workloads. So okay. Yeah. I think, do folks have like any other questions? Like Vikram, any final parting notes? Actually, yeah, I already see a question. Peter is asking, I'm interested in GDS, and I suspect that the benchmarks for that would polarize the GPUs into the ones that are forced use compatibility mode versus the ones that are using GPU direct storage.
Peter, I work actively on GDS, so can you elaborate more about your question?
I guess while Peter is typing, Eric is saying, I guess the first thing is even just detecting on the user side whether you're too slow. Example, LMC prints an estimate for an MFU, which I don't think is actually calculated correctly for all GPUs. So a user at least can complain about being slow. Yeah, like this has certainly resonated with me quite a bit. Like just we've had small features in PyTorch, like the flop counter, for example, that have been very helpful for people. I do suspect we don't have like enough sort of easy to run tools for generally like how far away from like max flop versus max bandwidth. So I think yeah, so it's a good point overall.
Nsight Compute is a fantastic tool for this as well, and probably would be worth getting someone from the DevTools team who builds that to come do a talk here, because Nsight Compute and Nsight Systems are awesome tools that everyone should know how to use.
Jake, thanks for reminding. I'm going to talk to the Nsight team and bring them on board on this.
For sure.
They're based out of the same place where I sit, so they should be able to do it.
Absolutely. Because yeah, just building on that quick, because Nsight Compute is a tool for analyzing the performance of an individual kernel, and one of the first things it shows you on the top is like the speed of light thing that we've been talking about. It shows you like, okay, what percentage of the maximum compute throughput am I achieving, and what percentage of the maximum bandwidth am I achieving? Like those are the first two plots that you'll see on the top of an Nsight Compute profile, and that's another really good way to be able to go see this as well. Because some problems, like we partition the world into like compute bound and memory bound on that graph, right? But like, and then we kind of, the world is never quite as simple as it seems in slides. Like we even talked about, right, that like there's this third class that, you know, is latency bound, that doesn't really quite fit on that particular view of the world. And so in certain cases, things aren't quite as simple as I was saying about like, oh, it's just memory bound or compute bound. Like there are cases where it's kind of a mix, or it's latency bound, or and so Nsight Compute is a really handy tool for those more complex cases where it's harder to say kind of a priori what you think the speed of light should be. These tools can take a lot of that guesswork out of it.
I will say we are big fans of NCU on the group. Like we introduced NCU in like lecture 1, and pretty much
Awesome.
at least every lecture I've covered NCU. So that'd be pretty nutty. But I think like Eric is making a good point, which is that like just kind of like very dumb CLI based utilities that take in your Python inference.py or train.py and just like work, you know, with just like print stuff out to the console would be quite helpful. I think there's like a tools here and there, but yeah, like maybe just one centralized repo for a lot of these useful utilities. Oh, so Eric's also saying NCU just does that. Yeah, I think that's right. It prints a lot of stuff, I would say, like by default.
Yeah, that's fair.
I think what you're looking for is a easy readability of the log, something that actually wraps around the logs that come out, so that it becomes easy to make sense of the data that comes out of it. So I agree that there are rooms for improvement on some places on how we generate the data and how we represent, but also it also varies on each of the person who actually views the data too. So there is also a diversity problem on how people want to see the data. What NCU provides you is a capability to dump it in the required format of your choice with the format options, with the CSV or other options, and then build custom tools on top of it. If you want to don't do either of them, you can also use something even more natively like Cupty, which is an open source library that allows you to insert profiling on your code base at your location of your code that you're running and dump statistical data points from there and generate a viewpoint from that point too. So there are many ways of doing the profiling and analyzing across different platforms. And I think one of the best part is all of those is available to you.
So Vikram, I saw like Peter answered your question on GDS. Do you mind just also answering that? It's around laptop GPUs. Maybe I'll read the question if you can't pull it up. I'm interested in making laptop GPUs and other more entry-level GPUs more utilitarian for modeling and simulation, but I found that most of them don't have access to GDS.
Yeah, so the problem is not the GDS. Many of these GPUs do not have GPU direct capability. So I think that's a functionality feature that is only available in Tesla grade or in the higher end GPUs and not on the lower end. What I recommend is it is not something that any of us are making decision on this. So we won't be able to specifically answer why it is not present in certain class of GPUs and why it is present in certain other class of GPU. If it's interesting, I raise a request. That's a classic way to ask, hey, this is of our interest. This is the use case. This is how it's going to be used. Can you make this available on this set of GPUs? And when in due course of time, it will become available.
So where would be the right forum for people to sort of lodge complaints around features they'd like to see supported in the consumer GPUs? Because I imagine maybe the GDS GitHub repo or something, but if there is one, I'm not sure. But yeah, I'm curious because I do agree that for a lot of times, maybe there's some stuff that make it to the PyTorch forum. I personally will complain to Piotr Bielinski about certain things. But if there's sort of like a more formal, if there's like a better forum, I'd love to hear it.
Jake, do we have something on this?
That's a hard answer. That's a hard question to answer.
Yeah.
Hard to answer in a way that I feel will get you actually what you want. The NVIDIA DevZone forums is one place.
Yep.
If you happen to work at a company or with a group that happens to work with an NVIDIA SA or salesperson or developer relations person, that is obviously not everyone's going to have the opportunity, but if you do, that is a way that will much more likely have its way of making its way to the people who make such decisions, is to complain through those channels.
Yep.
Those kinds of decisions are many levels above any of us here.
Yeah. So, and Peter, I want to be very specific to your answer too. So I just went over all over the place to give you an answer, but I want to be very direct on the GDS side, whether you want to use GDS or not. I understand that you want to enable GPUs to access the storage in a fast, streamlined fashion, but GDS does, the use case of GDS for that requires a bit more data point, because GDS fundamentally addresses only a buffer that you allocate in the CPU side of things. So what happens is that if you are limited by the CPU throughput while moving the data, doing memcopy data from your storage to your CPU memory and from CPU memory to your GPU, it only addresses by allowing you to copy the data from your storage to GPU memory directly. So if you don't have anything, if you're getting bounded by the CPU memory bandwidth kind of a throughput or CPU core count throughput, then those are the cases where you will find beneficial of using GDS. Even otherwise, even if you do not use GDS, you can actually create a fancy memory allocator that basically allows you to do the migration between your SSD, your CPU memory, and the GPU memory, and do overlap computation really efficiently. And this will be a bit more engineering effort. It's not automatic, but hey, it's fun too.
Yeah, like I suspect a lot of these, like, because I have heard similar asks, like as far as like making CPU offloading like a bit faster. And so there, like the use case is like, you don't have enough VRAM, but you can't easily plug in another GPU because your PSU doesn't support it, and well, yada yada. And you want to just like efficiently like offload stuff, but like offloading is quite slow. So people, I think, are pretty curious about ways of making it not slow, at least like within the GPU poor communities. All right, I guess that might be like a good time to end. Jake, Georgie, thank you as always. This was a wonderful talk. I really enjoyed it. I learned a lot. Vikram, thank you so much for the helpful comments. I do agree that like a natural follow-up lecture might be something more around profiling. We've had many profiling focused talks in the past, and I've gotten private feedback multiple times that those were people's favorites. So that just sounds wonderful.
Okay.
Thank you so much, everyone.
Yeah, I
And-
think, Mark, I would require to schedule 2 sessions, one dedicated for NCU and another dedicated for Nsight systems. And I believe, I would hope that they will also cover how to do it on your code base by adding NVTX markers and whatnot. So I'll talk to them. There are tons of techniques that you can do on profiling side.
Sounds wonderful to me. Thank you, Vikram. And thanks, everyone. See everyone soon. Goodbye.
Goodbye.